Yeah.
Okay, so we have to finish up this foldable on Riemann sums. So the last one we needed was trapezoid sum. So just like we had talked about before, we're gonna draw in some trapezoids on this curve so that we can find its area. So we're gonna have 6 trapezoids because we had 6 sub-intervals. So here our trapezoids will be sideways. They'll look something like this. This will be our base 1, this will be our base 2, and this will be our height. If you remember, the area of a trapezoid is 1/2 base 1 plus base 2 times its height. So we draw in our trapezoids. Alright, so now we start calculating the area of each of these trapezoids. For the very first one, all of them have a height of 2. So if we follow the formula, it's 1/2. The height for all of them will be 2, so we'll leave that on the outside. And then our very first base is 2 plus 2 times, if you look at this one, it's the second base for the first trapezoid, and then it becomes the first base for the second trapezoid. So I'm just going to put a 2 in the front and then multiply by that height, which in this case is 9 plus 2 times 7 plus 2 times 4. No, that's not a 4, that's actually a 3. Plus 2 times 2 plus 2 times 4. And then lastly, plus 2 times, or plus 8, because the last one is our last base 2. So you would multiply on the outside, which would give us 1, times we would add all of this here, and that'll give us an area of 70 units squared. And that's how you find trapezoid sums. But if you look at the notes that I gave you, it goes into a little more detail. It is a much more accurate way to approximate area beneath of a curve. And then it goes into finding the formula for the area of a trapezoid. This part right here is extremely important. Trapezoidal rule will overestimate a curve that is concave up, and it'll underestimate functions that are concave down. So then let's look at example 1. Approximate the area beneath this function on this interval using the trapezoid rule with 5 trapezoids. So just like we did with left-hand sums and right-hand sums, we need to find, in this case, our height of our trapezoids first. So we take our interval and divide it by the sub-intervals, which gives us 3/5. So if we look at our intervals, it'll go from 0 to 3/5, 6/5, 9/5, 12/5, and finally to 3. If we draw them out, we've got 1, 2, 3, 4, 5 trapezoids. We have to find the area of each one. So if we follow the formula, it's 1/2 times our height, which is constant, which is our 3/5, and then times each of our bases. 1 plus 2 times whatever f of 3/5 is when we substitute it into our function, plus 2 times the y value of plugging in 6/5, and so on and so forth. Remember that the very last one, you don't multiply it by 2 because it's only one base that you're going to use it for. So substituting these values into the x gives you these values. You add up everything inside, you multiply on the outside, then you finally multiply at the very end, gives you a fraction. If you simplify that, it'll give you a total area of 12.18 units squared. Let's look at another example. Approximate the area beneath y equals sine x on the interval from 0 to pi using the trapezoidal rule with n equal to 4 trapezoids. Find the interval first. Pi minus 0 divided by 4 gives us pi over 4. So our intervals for our trapezoids will be from 0, pi over 4, pi over 2, 3 pi over 4, and pi. Plug in each of these values so that we can find our base 1s and our base 2s. That's what we have here. To find the total area, it's 1/2 times our constant height times each of our bases. And remember that the inner ones, we multiply them by 2 because they become base 1 for our first trapezoid and our base 2 for our first trapezoid and our base 1 for our second trapezoid. Simplifying this, we end up with square root of 2 plus another square root of 2, which we can then write as 2 plus 2 square root of 2. Factor out a 2, so we'll have 2 pi over 8, 1 plus square root of 2. 2 pi over 8 simplifies to pi over 4. The inside stays the same. We multiply them on a calculator. It'll approximate to 1.0896 units squared. Let's look at another example. Use the trapezoidal rule to approximate the integral from 0 to 2 of x cubed for n is equal to 4. Here they didn't give us a graph for us to draw out, but as it was previously said on another video, you really don't need to draw out the function. You really only need the boundaries and the subintervals that we would need. So we find our height first, so 2 minus 0 divided by 4, which gives us half. So our intervals will go 0, half, 1, 3 over 2, and 2. We plug in our intervals into our function to find out our bases, and then we can calculate the area. Half from the formula times half from our height times our base 1s plus our base 2s. We calculate the inside, we multiply the outside, we simplify it, gives us 17 over 4 units squared. And the last example on trapezoidal rule. The function f is continuous on the interval from 2 to 8, and it has values shown in the table below. Use 3 subintervals to find the trapezoidal approximation of the integral from 2 to 8 of the function. Well, if we look at the function, or the table given to us first, if we look at our x values, it's not a constant change as it was in our previous ones, which is kind of what a note that's on to this side. The change in x is not constant on this interval. So we're going to have to calculate the area of the trapezoids separately and then add them up. So we're going to take the area of the trapezoid between 2 and 5, and then between 5 and 7, and between 7 and 8. So for the very first one, our change in x is the 3. The half is from the formula. Then we take our base 1 plus our base 2. Multiply all that out, gives us 51. Do the same thing
30 seconds.
Between 5 and 7. Same thing between 7 and 8. We get 3 areas. Add them up, gives us a total area of 144 units squared. And that is all on the trapezoidal rule.